Hello there. I'm so glad you found your way here tonight. Wherever you are in the world right now, allow yourself to settle into this shared moment of stillness. Let the noise of the day fade away. Let your thoughts grow quiet, like the soft hum of particles drifting through the unseen fabric of space. Right now, as you listen to these words, something extraordinary is happening all around you. At scales too small for any eye to see, the universe plays by different rules. Rules where particles can exist in many places at once. Where observation changes what is observed. Where two objects can remain connected across the vastness of space, communicating without signals. Tonight we journey into the strange and beautiful realm of quantum physics. A world that lies beneath everything you see and touch, yet behaves in ways that challenge our deepest intuitions about reality. We will explore how energy comes in tiny packets, how matter can act as both wave and particle, and how the very act of measuring changes what is measured. We will discover particles that tunnel through solid barriers, fields that bubble with invisible energy, and connections that link distant corners of the cosmos. All of it waiting to be shared in the stillness. Tonight, let's drift off together, while exploring over 100 soothing facts about quantum physics. There's no rush here, no test at the end. Just soft words and quiet wonders to carry you into rest. Welcome to Drowsy Discovery. I am glad you found your way here tonight. Perhaps you have had a long day. Perhaps you simply enjoy falling asleep to thoughts about the hidden machinery of reality. Either way, this space is for you. There is something deeply calming about contemplating the quantum world. Every atom in your body follows these strange rules. Every photon of light that reaches your eyes has traveled as both wave and particle. The very stability of matter itself depends on quantum principles that seem to defy common sense. You are connected to this story more than you might realize. The electrons that hold your atoms together, the energy that powers your cells, the light that carries images to your eyes, all of it obeys the quiet laws of the quantum realm. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is relax. So settle in. Let your breathing slow. And let the weight of the day drift away like a wave function dissolving into peaceful possibility. The quantum world is patient beyond measure. Particles wait in superposition for observation to arrive. Entangled pairs hold their connection across any distance. Virtual particles flicker in and out of existence in the tiniest fractions of a second. And yet, within all that strangeness there is profound order. Equations that predict outcomes with extraordinary precision. Patterns that repeat across every experiment. A hidden architecture beneath reality that we are only beginning to understand. Tonight, we will wander through this magnificent invisible world. We will meet the forces that shape atoms and the mysteries that still puzzle the greatest minds. But there is no hurry. The quantum realm has been here since the beginning of time. It can wait a little longer while you rest. Let us begin with the strange rules that govern the smallest scales. The rules of physics change dramatically at tiny scales. At the everyday scale of human experience, the laws of classical physics govern motion, gravity, and energy with elegant predictability. A thrown ball follows a parabolic arc, planets orbit in ellipses, and cause precedes effect in neat, orderly fashion. Yet as we descend into the realm of atoms and subatomic particles, these familiar rules give way to something far stranger. Objects no longer travel along definite paths, but spread out like waves. Particles can exist in multiple states simultaneously until observation forces a choice. The very act of measuring changes what is being measured. Quantum mechanics describes this microscopic world with extraordinary precision, yet its implications challenge our deepest intuitions about reality. The transition between the classical and quantum realms remains one of the great puzzles of modern physics. What seems solid and certain at human scales dissolves into probability and possibility at the smallest levels of existence. Quantum physics governs a world we can never directly see. No human eye will ever witness an electron orbiting an atomic nucleus or a photon traversing the vacuum of space. The scales involved are so fantastically small that they lie far beyond the reach of any microscope or imaging device. An atom is roughly 1/10 billionth of a meter across, and the particles within are smaller still. Yet despite this invisibility, quantum mechanics allows us to describe and predict the behavior of these entities with astonishing accuracy. We infer their properties through ingenious experiments that reveal interference patterns, energy spectra, and statistical distributions. The equations developed over the past century have been tested countless times and have never failed. This indirect knowledge is no less real for being unseen. We trust in quantum physics because it works, delivering technologies from lasers to transistors that depend on rules we can never observe directly. Energy does not flow smoothly but arrives in tiny packets called quanta. In the classical view, energy flows like water from a tap, able to take any value along a continuous spectrum. This assumption works well for everyday phenomena, but breaks down utterly at atomic scales. Max Planck discovered in 1900 that the only way to explain the radiation emitted by hot objects was to assume energy came in discrete bundles. These packets, or quanta, are measured by a tiny constant that now bears Planck's name. The realization that energy is granular rather than smooth was the first step into the quantum world. It explained why atoms do not collapse and why matter has stable structure. Every transfer of energy, whether in light or heat or chemical bonds, involves whole numbers of these fundamental units. This simple idea reshaped the entire foundation of physics and opened the door to a century of discoveries. Light can behave as both a wave and a particle. For centuries, scientists debated whether light was a stream of particles or a wave rippling through space. Experiments seem to support both views at different times. Isaac Newton favored particles, while later experiments on interference and diffraction firmly established the wave nature of light. Then, in the early 20th century, Einstein showed that the photoelectric effect could only be explained if light arrived in discrete packets called photons. Each photon carries a fixed amount of energy determined by its frequency, behaving very much like a particle. Yet the same light also produces interference patterns that only waves can create. This duality is not a contradiction, but a fundamental feature of nature. Light is neither purely wave nor purely particle. It transcends both categories, revealing one aspect or the other, depending on how we choose to observe it. Wave-particle duality lies at the heart of quantum mechanics. Electrons also display this puzzling wave-particle duality. Initially, wave-particle duality was thought to apply only to light. Electrons, being tiny bits of matter with measurable mass and charge, seemed firmly in the particle category. Then Louis de Broglie proposed that all matter possesses a wavelength, inversely proportional to its momentum. Experiments soon confirmed this prediction when electrons passing through thin crystals produced diffraction patterns identical to those of X-rays. The electron, once considered a simple point-like particle, was revealed to spread out like a wave, interfering with itself under the right conditions. This discovery generalized duality from light to all quantum objects. Atoms, molecules, and even larger structures have been shown to exhibit wave behavior in sufficiently sensitive experiments. The boundary between wave and particle dissolves entirely at the quantum level. Every entity in the subatomic world carries both identities, switching between them according to the nature of the experiment. The act of observation can change how a quantum system behaves. In the classical world, observation is passive. Looking at a planet does not alter its orbit, and measuring the length of a table leaves the table unchanged. Quantum mechanics overturns this intuition entirely. At the smallest scales, any measurement requires an interaction, typically the exchange of at least one quantum of energy. This unavoidable disturbance means that the very act of looking changes what is being looked at. Particles in superposition collapse to definite states upon measurement. Interference patterns vanish when we try to determine which path a particle took. The observer becomes an active participant in the outcome. Philosophers and physicists have debated for decades what this observer effect truly means. Some interpretations suggest that reality remains indeterminate until observed, while others propose that observation merely reveals pre-existing states. Whatever the answer, passive measurement is impossible in the quantum realm. The double-slit experiment reveals the heart of quantum strangeness. In this famous experiment, particles such as electrons or photons are fired at a barrier containing two narrow slits. On the far side, a detector records where each particle lands. If particles were simple bullets, we would expect two clusters directly behind the slits. Instead, an interference pattern emerges, with alternating bands of many hits and few hits, just as waves produce when they overlap. The astonishing part comes when we try to determine which slit each particle passed through. As soon as a detector watches the slits, the interference pattern vanishes, and particles behave like ordinary objects again. The mere possibility of knowing the path destroys the wave behavior. Richard Feynman called this experiment the heart of quantum mechanics because it encapsulates wave-particle duality, superposition, and the observer effect in a single elegant demonstration. No classical explanation can account for the results. Nature forbids us from knowing certain properties with perfect precision. In classical physics, any property of a system can in principle be measured to arbitrary accuracy. Given sufficiently sensitive instruments, we can know a ball's position and velocity as precisely as we wish. Quantum mechanics places an absolute limit on this knowledge. Certain pairs of properties, called conjugate variables, cannot both be known precisely at the same time. The more accurately we determine one, the more uncertain the other becomes. This is not a failure of technology, but a fundamental feature of nature. The universe itself does not possess definite values for both properties simultaneously. Position and momentum form one such pair. Energy and time form another. This built-in fuzziness protects the stability of atoms and prevents electrons from spiraling into nuclei. Nature's refusal to yield perfect knowledge is woven into the very fabric of reality. The Heisenberg uncertainty principle limits what can ever be measured. Formulated by Werner Heisenberg in 1927, this principle quantifies nature's built-in blurriness. It states that the product of the uncertainties in position and momentum can never be smaller than a fixed fraction of Planck's constant. No experiment, no matter how ingenious, can violate this bound. The uncertainty is not due to clumsy instruments or hidden flaws in our methods. It is intrinsic. At human scales, Planck's constant is so tiny that the fuzziness is undetectable. At atomic scales, it dominates. Electrons in atoms do not occupy sharp orbits, but spread out into probability clouds, whose shape reflects the balance between confinement and momentum. The Heisenberg principle has been tested countless times and never breached. It remains one of the most precisely confirmed laws in all of physics, setting an ultimate boundary on what can ever be known. A particle can exist in many states at the same time. Superposition is perhaps the most counterintuitive feature of quantum mechanics. A particle does not have to choose a single position, spin, or energy until a measurement forces the issue. Before that moment, it exists in a blend of all possible states, each with a certain probability amplitude. The electron in an atom, for instance, is not located at any particular point, but smeared across a cloud of possibilities. This is not ignorance on our part. The particle genuinely lacks a definite state. Mathematical formalism describes superposition with wave functions, complex valued expressions that encode every potential outcome. Only when we observe the system does the wave function collapse to a single result. This strange ability to be in many configurations at once underlies quantum computing and cryptography. Superposition is not metaphor. It has measurable consequences confirmed by experiment after experiment. Superposition is not just theory, but confirmed by countless experiments. Skeptics once wondered whether superposition was merely a convenient mathematical fiction or a genuine feature of the physical world. Decades of painstaking experiments have removed all doubt. Interference patterns in the double-slit experiment reveal superposition directly, as does the phenomenon of quantum beats in atomic spectroscopy. More recently, researchers have placed ever larger objects into superposition states, including molecules containing thousands of atoms. Each success pushes the boundary between the quantum and classical worlds further into new territory. Superposition has practical applications in quantum computing, where information is encoded in states that exist as both 0 and 1 simultaneously. It enables quantum cryptography protocols that would be impossible classically. The experimental confirmation of superposition stands as one of the great triumphs of modern physics, demonstrating that nature makes use of possibilities we once thought impossible. Reality is built from probabilities rather than certainties. Classical physics aspired to a clockwork universe where, given perfect knowledge of initial conditions, every future event could be predicted. Quantum mechanics shattered this dream. Even with complete information about a quantum system, its future behavior can only be described in terms of probabilities. The equations predict the likelihood of outcomes, but never guarantee which outcome will occur. This probabilistic character is not a reflection of incomplete knowledge, it is fundamental. Einstein famously objected that God does not play dice, yet every experiment has confirmed that nature is genuinely random at its deepest level. Radioactive decay, photon emission, and particle interactions all follow statistical laws without underlying determinism. This built-in randomness has profound implications for philosophy, challenging notions of causality and free will. Reality, it seems, is woven from probabilities rather than fixed certainties. Wave functions encode all possible outcomes before measurement. The mathematical object at the heart of quantum mechanics is the wave function, typically denoted by the Greek letter psi. It contains everything knowable about a quantum system, representing not a single state but a superposition of all possible configurations, weighted by probability amplitudes. The square of the amplitude for each outcome gives the probability that this outcome will occur upon measurement. Unlike classical descriptions that assign definite values to every property, the wave function holds all options open until observation intervenes. It evolves smoothly in time according to the Schrödinger equation, spreading and interfering like a wave. This elegant mathematics predicts experimental results with stunning precision. Yet interpreting what the wave function actually represents remains controversial. Some view it as a real physical entity. Others consider it merely a tool for calculating probabilities. Either way, it encodes the full spectrum of possibility waiting to become reality. How possibilities collapse into a single reality remains a mystery. Whenever we measure a quantum system, the wave function abruptly changes from a spread of possibilities to a single definite outcome. This transition, often called wave function collapse, is instantaneous and irreversible. Before measurement, the electron might be here or there. Afterward, it is precisely here. Yet the mechanism behind this collapse remains deeply mysterious. The Schrödinger equation, which governs quantum evolution, is smooth and deterministic. It contains no provision for sudden jumps. Different interpretations of quantum mechanics offer competing explanations. Some propose that the observer's mind triggers collapse, others that collapse is an approximation of deeper processes, and still others that collapse never happens at all, because every outcome occurs in branching parallel worlds. No experiment has yet distinguished between these views. The measurement problem, as it is known, remains one of the deepest unsolved puzzles in physics. Schrödinger's cat illustrates the paradox of quantum superposition. Erwin Schrödinger devised his famous thought experiment to highlight the absurdity of applying quantum rules to everyday objects. A cat is placed in a sealed box with a radioactive atom, a detector, and a vial of poison. If the atom decays, the detector triggers the poison and kills the cat. Quantum mechanics says the atom exists in a superposition of decayed and not decayed until observed. Logic then implies the cat is also in a superposition of alive and dead until the box is opened. Schrödinger intended this scenario as a reductio ad absurdum, arguing that superposition cannot extend to macroscopic objects. Yet the thought experiment has become a cultural icon, prompting serious research into where the quantum classical boundary lies. Modern experiments push superpositions into ever larger systems, edging closer to the scale of living organisms. The cat remains a symbol of the unresolved mystery at the heart of measurement. Two particles can share the same existence across vast distances. Quantum entanglement links particles together in ways that have no classical analog. When two particles become entangled, their properties become correlated regardless of the distance separating them. Measuring one instantly determines the outcome for its partner, even if that partner lies on the other side of the universe. This is not because information travels between them. Rather, they share a single, indivisible quantum state that cannot be described as two separate entities. The phenomenon arises naturally when particles interact and exchange quantum numbers. Once entangled, the pair behaves as a unified whole. Entanglement is essential for quantum computing, cryptography, and teleportation protocols. It demonstrates that the universe contains connections deeper than local cause and effect. Two entangled particles, once described by a joint wave function, remain forever intertwined until the entanglement is broken by measurement or interaction with the environment. Entangled particles respond to each other instantly, regardless of separation. The correlations between entangled particles are established the moment they are measured, no matter how far apart they may be. Experiments have confirmed this instantaneous connection over distances exceeding 1,000 kilometers using satellite-based links. The speed of light poses no barrier because no signal carrying usable information passes between the particles. What travels is not a message, but a correlation embedded in the shared quantum state. Einstein considered this non-locality deeply troubling, believing that nature should obey local realism, where distant events cannot influence each other faster than light. Yet experiment after experiment has vindicated quantum predictions. The correlations are real, and they appear without any delay attributable to communication. This instant responsiveness is one of the strangest features of entanglement, showing that quantum reality is more interconnected than any classical picture allows. Einstein called this connection spooky action at a distance. Albert Einstein, despite his foundational contributions to quantum theory, never accepted its implications about non-locality. In a famous paper co-authored with Boris Podolsky and Nathan Rosen, he argued that entanglement implied either faster-than-light influence or hidden variables that predetermined outcomes. He dismissed the instantaneous correlations as spooky action at a distance, a phrase that has endured in popular culture. For Einstein, the universe should be local and realistic, with properties existing independently of observation. Decades later, John Bell devised inequalities that could distinguish between hidden variables and true quantum entanglement. Experiments consistently violated Bell's bounds, vindicating quantum mechanics and ruling out local hidden variables. The spooky action Einstein mocked turned out to be a genuine feature of reality. His discomfort underscores how profoundly quantum mechanics challenges our classical intuitions about space, time, and causation. Experiments have confirmed that entanglement is real and unbreakable. Since the first tentative tests in the 1980s, experimenters have closed loophole after loophole to confirm quantum entanglement beyond reasonable doubt. Early experiments left small gaps that critics suggested might allow classical explanations. Subsequent efforts eliminated detection inefficiencies, ensured genuine random measurement choices, and separated the particles so far that no signal could travel between them before measurements were complete. In 2015, a landmark experiment closed all major loopholes simultaneously, earning its authors widespread acclaim. Satellite-based experiments followed, demonstrating entanglement over distances exceeding 1,200 kilometers through the vacuum of space. These results leave no room for local hidden variable theories. Entanglement is not a trick of statistics or a flaw in experimental design. It is a robust feature of nature. The correlations predicted by quantum mechanics have been verified to extraordinary precision, cementing entanglement as a pillar of modern physics. No hidden mechanism can explain these strange quantum correlations. Before Bell's work, some physicists hoped that entanglement could be explained by hidden variables, unseen factors that predetermined outcomes, and made the correlations only seem instantaneous. John Bell showed in 1964 that any such theory must satisfy certain statistical inequalities. Quantum mechanics predicts violations of those inequalities, and experiments have consistently observed those violations. This rules out a wide class of alternatives to quantum mechanics, any theory that is both local and realistic. The correlations we observe cannot be explained by secretly prearranged answers, or by any signal traveling through space at or below the speed of light. The universe simply does not work that way. These results have profound philosophical implications, suggesting that reality is non-local, or that definite properties do not exist before measurement. Either way, the hidden mechanism loophole is firmly closed. Bell's theorem proved the universe does not behave classically. John Bell's theorem stands as one of the most important results in the foundations of physics. It demonstrates mathematically that no theory based on local hidden variables can reproduce all the predictions of quantum mechanics. When experiments confirmed that quantum predictions were correct, the classical worldview suffered a decisive blow. The universe does not behave like a clockwork mechanism with definite, predetermined states awaiting discovery. Instead, properties are created by observation, and correlations between distant particles transcend the bounds of local cause and effect. Bell's theorem transformed entanglement from a philosophical curiosity into a testable prediction, with clear empirical consequences. Its violation in the laboratory proved that nature is stranger than even Einstein imagined. The theorem continues to inspire new research, informing interpretations of quantum mechanics and guiding the development of quantum technologies. Quantum teleportation can transfer a particle's identity to another location. Despite its science fiction name, quantum teleportation is a real and well-tested phenomenon. It does not transport matter, but rather transfers the complete quantum state of one particle to another at a distant location. The process requires an entangled pair shared between sender and receiver, plus a classical communication channel. When the sender measures the original particle, along with one member of the entangled pair, the result is transmitted classically to the receiver, who then applies the corresponding operation to recreate the original state. The original particle loses its identity in the process. No copy is made. Teleportation has been demonstrated in laboratories and across satellite links spanning thousands of kilometers. It is essential for future quantum networks and distributed quantum computing. Though we cannot teleport people, the transfer of quantum information across vast distances opens extraordinary possibilities. Some physicists believe spacetime itself emerges from entanglement. One of the most intriguing ideas in modern theoretical physics is that the smooth fabric of spacetime is not fundamental, but emerges from deeper quantum structures. According to this view, entanglement between microscopic degrees of freedom weaves the geometry of space. When regions are highly entangled, they appear close together. When entanglement is weak or absent, they seem far apart. Research in string theory and the holographic principle has lent support to this conjecture. The ER equals EPR proposal, for instance, suggests that wormholes and entanglement are two manifestations of the same phenomenon. If spacetime is indeed built from entanglement, then gravity itself would be a consequence of quantum information. These ideas remain speculative, but they offer a tantalizing glimpse of how quantum mechanics might ultimately unify with general relativity in a theory of quantum gravity. The universe may be woven together by invisible quantum links. If entanglement underlies the structure of spacetime, then every point in the cosmos is connected through a web of quantum correlations. These invisible links would not transmit signals faster than light, but they would bind distant regions in subtle ways that classical physics cannot describe. The idea recasts the universe, not as a collection of separate objects, but as a single, unified quantum system. Such a picture aligns with certain interpretations of cosmology, where the entire observable universe began in a highly correlated state after the Big Bang. As the cosmos evolved, these primordial entanglements may have spread and diversified, seeding the structures we observe today. The notion of a quantum entangled universe remains speculative yet profoundly inspiring. It suggests that separation is an illusion, and that everything, at its deepest level, is connected. Entanglement can persist even in noisy and chaotic environments. Early critics worried that entanglement would be too fragile to survive outside the controlled conditions of a laboratory. Any interaction with the environment, they argued, would destroy the delicate quantum correlations. While decoherence is indeed a challenge, researchers have found ways to protect and extend entanglement under surprisingly harsh conditions. Error correction protocols can detect and repair damage to quantum states. Certain materials and configurations exhibit unusually long coherence times. Experiments have transmitted entangled photons through turbulent atmosphere and noisy optical fibers across hundreds of kilometers. Satellite links preserve entanglement, even as photons traverse the vacuum of space between Earth and orbit. Warm biological systems may also sustain quantum coherence, though this remains an active area of research. The resilience of entanglement is essential for practical quantum technologies. What once seemed impossibly delicate now appears robust enough for real-world applications. Electrons have no measurable size, yet spread out like clouds. As far as our most precise experiments can determine, the electron is a point particle with no detectable internal structure. Collider experiments have probed distances a billion times smaller than an atom without finding any hint of substructure. Yet this zero-size entity does not occupy a single point. Quantum mechanics describes the electron as a probability cloud, smeared across a region of space according to its wave function. In an atom, this cloud takes on specific shapes called orbitals, with lobes and nodes determined by quantum numbers. The electron is simultaneously nowhere and everywhere within this cloud until measured. Its apparent size arises not from internal structure, but from the quantum fuzziness of its wave function. This strange duality between point-like identity and spread-out probability is a hallmark of the quantum world. Photons carry no mass, yet can push objects through space. Light has no rest mass. A photon at rest is a contradiction in terms. Photons always travel at the speed of light. Despite this masslessness, photons carry energy and momentum. When they strike a surface, they exert pressure, a tiny push that can move objects. This radiation pressure has been measured in laboratories and forms the basis of proposed solar sails that would propel spacecraft using nothing but sunlight. The momentum of a photon is related to its wavelength. Shorter wavelengths carry more momentum. High-energy gamma rays push harder than low-energy radio waves. Even though individual photons deliver negligible force, the trillions of photons from the Sun add up to measurable effects. Light-pushing matter seems paradoxical to classical intuition, yet it is a direct consequence of the energy-momentum relationship in quantum mechanics and relativity. Billions of neutrinos pass through your body every second unnoticed. Neutrinos are among the most ghostly particles in existence. They interact so weakly with ordinary matter that they can pass through entire planets without deflection. The Sun alone sends trillions of neutrinos streaming through every square centimeter of Earth each second. Right now, as you read these words, vast numbers of them are slipping through your body as if it were not there. Detecting neutrinos requires massive detectors buried deep underground to shield against other particles. When a neutrino does interact, the event is extraordinarily rare. Neutrinos come in 3 types, or flavors, and can oscillate between them as they travel. This oscillation implies that neutrinos have a tiny but non-zero mass, a discovery that earned the Nobel Prize. Their elusive nature makes them difficult to study, yet invaluable for probing the universe's hidden workings. Quarks are forever trapped together and can never exist alone. Unlike electrons and photons, quarks cannot be isolated. They are bound together by the strong nuclear force, mediated by particles called gluons, which grow stronger as quarks try to separate. Attempt to pull two quarks apart, and the energy poured into the separation eventually creates new quark-antiquark pairs that recombine into new particles. This phenomenon, called confinement, means that quarks always come packaged in twos or threes, forming mesons and baryons such as protons and neutrons. No experiment has ever detected a free quark, despite decades of searching. Quarks also carry a property called color charge, distinct from electric charge, which governs their interactions. Confinement makes the study of quarks indirect, relying on high-energy collisions and the debris they produce. The strong force is aptly named. It is the mightiest interaction in nature. Gluons carry the strongest force in the universe. The strong nuclear force, also called the strong interaction, holds atomic nuclei together and binds quarks within protons and neutrons. Its messengers are particles called gluons, massless entities that carry color charge themselves. Unlike photons, which carry no electric charge, gluons interact with one another, making the strong force far more complex than electromagnetism. At very short distances, quarks move almost freely, a regime known as asymptotic freedom. But at larger separations, the force skyrockets, ensuring quarks remain confined. Gluons contribute significantly to the mass of protons and neutrons, even though quarks themselves are surprisingly light. The energy stored in gluon fields accounts for most of the visible mass in the universe. Understanding gluon dynamics remains an active frontier of research, with particle colliders probing the gluon-rich interior of protons. The Higgs boson gives particles their mass. For decades, physicists wondered why some fundamental particles have mass, while others, like the photon, do not. The answer came with the Higgs mechanism, proposed in the 1960s by several theorists including Peter Higgs. According to this theory, an invisible field permeates all of space. Particles that interact strongly with this field acquire mass, those that do not remain massless. The Higgs boson is the quantum excitation of this field, a ripple that can be detected in high-energy collisions. In 2012, the Large Hadron Collider announced the discovery of a particle matching the predicted Higgs boson, confirming the mechanism at last. The discovery completed the Standard Model of particle physics, the most successful theory ever devised for describing matter and forces. The Higgs field explains why matter has mass and why the universe is not filled with pure radiation. Empty space is not truly empty, but seethes with virtual particles. The vacuum of space, devoid of matter and light, might seem like the purest form of nothingness. Quantum field theory reveals otherwise. Even in perfect emptiness, fields fluctuate constantly, and these fluctuations give rise to fleeting pairs of particles and antiparticles. Called virtual particles, they pop into existence and annihilate one another within timescales too brief to measure directly. Their existence is inferred from real effects, such as the Lamb shift in atomic spectra and the anomalous magnetic moment of the electron. The vacuum is a restless sea of potential, influencing real particles that pass through it. Virtual particles are not mere mathematical abstractions, they have measurable consequences. The concept challenges our intuition about emptiness and suggests that the foundation of reality is far more dynamic than it appears. The quantum vacuum contains a background of zero-point energy. Quantum mechanics forbids any system from reaching absolute stillness. Even at the lowest possible temperature, particles retain a residual motion called zero-point energy. The same principle applies to quantum fields. The vacuum cannot sit perfectly motionless. These unavoidable fluctuations imbue empty space with a baseline energy density that never goes to zero. Attempts to calculate this energy using quantum field theory yield absurdly large values, far exceeding the energy observed in the universe. This mismatch, known as the cosmological constant problem, remains one of the biggest puzzles in physics. Despite the discrepancy, zero-point energy has real physical effects. It contributes to forces between closely spaced surfaces, influences atomic transitions, and may play a role in the accelerating expansion of the cosmos. The energy of nothingness is not nothing at all. Experiments continue to probe how zero-point fluctuations shape the behavior of matter and the structure of space itself. Antimatter is the perfect mirror, opposite of ordinary matter. For every particle in the Standard Model, there exists an antiparticle, with the same mass but opposite charge, and quantum numbers. The electron has the positron. The proton has the antiproton. When particle and antiparticle meet, they annihilate in a flash of energy, converting their mass entirely into photons or other particles. Antimatter is not science fiction, but is produced routinely in particle accelerators, and even in certain medical imaging devices. The mystery lies in its scarcity. The Big Bang should have created equal amounts of matter and antimatter, yet the universe today is overwhelmingly matter-dominated. This imbalance, called baryon asymmetry, remains unexplained. Understanding why antimatter lost out may reveal physics beyond the Standard Model. For now, antimatter stands as a perfect mirror image that nature somehow chose to suppress. Matter can be created from pure energy and converted back again. Einstein's famous equation relates mass and energy as two forms of the same substance. In particle accelerators, kinetic energy is transformed directly into new particles when beams collide. The heavier the particles created, the more energy required. When a particle meets its antiparticle, the reverse occurs. Mass vanishes, and energy erupts in the form of photons or other light particles. These transformations are not metaphors but measurable realities observed countless times. Pair production, where a high-energy photon converts into an electron-positron pair, demonstrates energy becoming mass. Annihilation demonstrates the converse. The equivalence underpins nuclear power and stellar fusion, where tiny mass deficits release enormous energy. Matter and energy are interchangeable currencies, traded at rates set by the speed of light squared. Every particle is a ripple in an invisible underlying field. Quantum field theory describes particles not as tiny balls, but as excitations of fields that permeate all of space. The electron field exists everywhere. When disturbed in a particular way, it manifests as an electron. The photon field behaves similarly, producing photons when energy passes through it. Each type of particle corresponds to its own field, and interactions occur when fields couple together. This picture unifies the particle and wave aspects of matter, since fields are continuous while their excitations are quantized. It also explains how particles can be created and destroyed. Energy flows in or out of the field, raising or lowering the excitation level. Quantum field theory is the foundation of the Standard Model, and has produced predictions verified to extraordinary precision. Particles are not fundamental in themselves, they are the songs that fields sing. Quantum field theory unifies particles and forces into one framework. Before quantum field theory, particles and the forces between them were treated as separate concepts. Atoms were made of particles, forces were something else, vaguely described by fields or action at a distance. Quantum field theory merged these notions, showing that forces arise from the exchange of virtual particles between matter particles. Electromagnetism is mediated by photon exchange, the strong force by gluons, the weak force by W and Z bosons. This picture provides a unified mathematical language that describes all known particles and 3 of the 4 fundamental forces. The framework has been tested to extraordinary precision, correctly predicting quantities like the electron's magnetic moment to better than 1 part in a trillion. Quantum field theory is not just a theory, it is the scaffolding on which modern particle physics is built. Even in perfect vacuum, quantum fields are never completely still. Classical physics would predict that the vacuum, devoid of energy and particles, should be the stillest possible state. Quantum mechanics upends this expectation. The Heisenberg uncertainty principle ensures that no field can sit at exactly 0, because that would mean both its value and rate of change are precisely known. Instead, fields constantly jitter, fluctuating around their ground state. These vacuum fluctuations are not observable directly, but their effects are measurable. They shift the energy levels of atoms, influence the forces between nearby plates, and contribute to the tiny anomalous magnetic moments of particles. The vacuum is in perpetual motion, a sea of restless potential that underlies all physical phenomena. Even nothing, it turns out, is something. The Casimir effect shows that empty space can push objects together. When 2 uncharged metal plates are placed extremely close together in a vacuum, they experience a small but measurable attractive force. This is the Casimir effect, first predicted in 1948. The explanation lies in the vacuum fluctuations of the electromagnetic field. Between the plates, only certain wavelengths of virtual photons can exist, while outside, all wavelengths are allowed. This imbalance creates a net inward pressure, pushing the plates together. The effect has been measured in laboratories with high precision and matches theoretical predictions closely. It demonstrates that the quantum vacuum is not an abstraction, but a physical entity with real consequences. Some researchers speculate about harnessing vacuum energy for propulsion or power, though such applications remain far from practical reality. Zero-point energy exists throughout the entire universe. Every cubic centimeter of space, whether in the depths of intergalactic voids or the heart of a star, contains zero-point energy from quantum field fluctuations. This energy density is uniform and ever-present, a cosmic background that never turns off. Theoretical calculations of its magnitude produce extremely large numbers, far exceeding the energy density inferred from the universe's expansion. Reconciling theory and observation is one of the greatest unsolved problems in physics. Despite the mismatch, zero-point energy has real effects at small scales, influencing chemical reactions, atomic spectra, and material properties. It may contribute to the mysterious dark energy driving the universe's accelerating expansion. The zero-point field is an invisible reservoir of activity permeating all of existence, a foundation of energy underlying every atom and every void. The quantum vacuum may influence the shape of spacetime itself. General relativity tells us that energy curves spacetime. If the quantum vacuum contains energy, that energy should gravitate. Observations of the universe's expansion suggest a small cosmological constant, a term in Einstein's equations that acts like a repulsive pressure. Many physicists suspect this constant is related to vacuum energy, though the predicted and observed values differ by many orders of magnitude. Resolving this discrepancy could reveal new physics beyond current theories. Some speculative models propose that vacuum energy changes over time, or varies across space, influencing the evolution of the cosmos. Others suggest that vacuum fluctuations might seed tiny gravitational waves, or even contribute to the emergence of space-time itself. The intersection of quantum mechanics and gravity remains one of the deepest frontiers in physics. Extreme fields can twist and transform the nature of the vacuum. Under normal conditions, the quantum vacuum behaves in predictable ways, its fluctuations producing familiar effects. But in the presence of extremely strong electromagnetic or gravitational fields, the vacuum can undergo dramatic changes. Near magnetars, the most magnetic objects in the universe, vacuum polarization alters how light propagates, bending and splitting photons in exotic ways. Intense laser fields can create virtual electron-positron pairs that affect the propagation of probe beams. Close to black holes, the extreme curvature of space-time modifies vacuum behavior in ways still being explored. These extreme environments serve as natural laboratories, pushing quantum field theory to its limits. Understanding how fields reshape the vacuum provides clues to physics beyond the standard model and offers glimpses of conditions that existed in the earliest moments of the universe. Black holes slowly radiate energy through Hawking radiation. In 1974, Stephen Hawking combined quantum field theory with general relativity and made a startling prediction. Black holes are not perfectly black. They emit faint thermal radiation due to quantum effects near the event horizon. Virtual particle pairs constantly pop into existence throughout space. Near a black hole, one member of a pair can fall beyond the horizon while the other escapes. The escaping particle carries away energy, and from the outside it appears as if the black hole is radiating. Over unimaginably long timescales, this process causes black holes to shrink and eventually evaporate entirely. Hawking radiation is extraordinarily weak for stellar mass black holes, far too faint to detect with current technology. Yet its theoretical implications are profound, linking thermodynamics, gravity, and quantum mechanics in ways that remain incompletely understood. The energy of nothingness may be driving the universe apart. Observations since the late 1990s have revealed that the expansion of the universe is accelerating rather than slowing down. Something is pushing galaxies apart ever faster, and physicists call this mysterious influence dark energy. One leading candidate is the cosmological constant, a uniform energy density permeating all of space. If the quantum vacuum contributes to this constant, then the energy of nothingness would be responsible for the largest scale dynamics of the cosmos. Yet the calculated and observed values differ drastically, leaving the connection uncertain. Alternative theories propose dynamical fields or modifications to gravity, but none has been confirmed. Dark energy, whatever its origin, comprises roughly 2/3 of the universe's total energy. Understanding its nature may require new physics that bridges quantum mechanics and cosmology. The true nature of the quantum vacuum remains deeply mysterious. Despite decades of theoretical and experimental progress, the vacuum is still not fully understood. We know it is not empty, but filled with fluctuating fields that influence real particles and forces. We know it contains energy that should gravitate, yet attempts to calculate this energy produce answers far too large. We suspect it may play a role in dark energy, in the mass of particles via the Higgs mechanism, and perhaps in the emergence of space-time itself. Yet many puzzles remain. Why is the observed vacuum energy so small? How does the vacuum behave at the Planck scale where quantum gravity dominates? What new phenomena lurk in regimes we have yet to probe? The vacuum is not a blank canvas, but a rich, dynamic substrate whose mysteries continue to challenge the brightest minds in physics. Quantum computers use qubits that can be 0 and 1 simultaneously. Classical computers store information in bits, each of which is either 0 or 1. Quantum computers use qubits, which exploit superposition to exist in a blend of both states at once. This ability dramatically expands the computational space a quantum machine can explore. With just 100 qubits in superposition, a quantum computer can represent more states than atoms in the observable universe. When qubits are measured, they collapse to definite values, producing an answer. The challenge is designing algorithms that coax useful results from the superposition and entanglement. Errors from environmental noise are a major obstacle, driving research into error correction and fault tolerance. Despite these hurdles, small quantum processors have already demonstrated speedups on specific tasks. The ultimate goal is a scalable quantum computer capable of solving problems no classical machine could ever tackle. Qubits can store multiple answers in a single moment. Because a qubit exists in a superposition of states, a register of qubits can hold many possible values simultaneously. A 10-qubit register represents all 1024 possible combinations at once. This parallelism allows quantum algorithms to explore many solutions in a single step. Of course, measurement collapses the superposition to a single outcome, so the art of quantum computing lies in manipulating probabilities so that the right answer is likely to appear. Clever algorithms like Grover's search or Shor's factoring exploit interference to amplify correct solutions and suppress wrong ones. The ability to store and process multiple possibilities in parallel is what gives quantum computers their power. It is not magic, but a careful choreography of superposition, entanglement and interference that harnesses the strange rules of quantum mechanics for practical ends. Entanglement supercharges the power of quantum processing. Superposition alone does not fully explain the advantage of quantum computers. Entanglement is equally essential. When qubits are entangled, measuring one instantly constrains the state of the others, no matter how many there are. This correlation allows quantum algorithms to propagate information across the entire register in ways impossible for classical bits. Entanglement enables speedups in algorithms for search, optimization and simulation of quantum systems. It also underpins quantum error correction, where extra entangled qubits help detect and fix errors without collapsing the computation. Building and maintaining entanglement across many qubits is a major engineering challenge, requiring extreme isolation from environmental noise. Yet laboratories around the world are steadily increasing qubit counts and coherence times. As control improves, entanglement will increasingly fuel the computational power of tomorrow's quantum machines. Certain quantum algorithms could solve problems far faster than any classical machine. Peter Shor's algorithm, published in 1994, demonstrated that a sufficiently large quantum computer could factor large numbers exponentially faster than any known classical method. Since modern encryption relies on the difficulty of factoring, Shor's discovery sent shockwaves through cryptography and computer science. Grover's algorithm offers a quadratic speedup for searching unsorted databases. Other algorithms promise advantages for simulating molecules, optimizing logistics, and training machine learning models. Not every problem benefits from quantum speedup, but for those that do, the gains can be transformative. Building a quantum computer capable of running these algorithms at scale remains an enormous challenge, requiring millions of error-corrected qubits. Yet the potential payoff drives intense research and investment worldwide. Quantum supremacy, the demonstration that a quantum computer can outperform any classical supercomputer on a specific task, was first claimed in 2019. Quantum cryptography creates codes that cannot be cracked. Classical encryption relies on mathematical problems assumed to be hard, but an adversary with enough computational power could in principle break any code. Quantum key distribution offers a different kind of security, rooted in the laws of physics, rather than computational difficulty. Two parties share entangled photons or single photons prepared in superposition. Any attempt to eavesdrop disturbs the quantum states in detectable ways. If the channel is compromised, the disturbance reveals the intrusion, and the key is discarded. When the channel is secure, the parties obtain a shared secret key guaranteed by quantum mechanics to be unknown to anyone else. Quantum key distribution has been demonstrated over hundreds of kilometers of fiber and via satellites linking ground stations across continents. It represents a new era of communication security, one where physics itself guarantees privacy. Quantum sensors can detect the faintest whispers of change. Quantum systems are exquisitely sensitive to their environment, a property that makes maintaining coherence difficult, but opens exciting possibilities for precision measurement. Quantum sensors exploit superposition and entanglement to detect magnetic fields, gravitational variations, and electric signals with unprecedented accuracy. Atomic magnetometers can sense fields a trillion times weaker than Earth's magnetic field. Quantum gravimeters detect subtle variations in local gravity that reveal underground structures or changes in groundwater. Atomic clocks, themselves quantum devices, measure time so precisely that they can detect the gravitational redshift between floors of a building. These sensors have applications in navigation, geology, medicine, and fundamental physics. By harnessing the sensitivity that makes qubits fragile, engineers transform a liability into an asset, turning quantum noise into precision instruments. Superconductors allow electricity to flow forever without resistance. Below a critical temperature, certain materials undergo a dramatic transition. All electrical resistance vanishes. Current can circulate through a superconducting loop indefinitely, without any applied voltage or loss of energy. This phenomenon, discovered in 1911, arises from quantum mechanics. Electrons pair up and condense into a collective state described by a single wave function. Collisions that would scatter individual electrons have no effect on this coherent state. Superconductors expel magnetic fields from their interior, a phenomenon called the Meissner effect, enabling magnetic levitation. They are essential components in MRI machines, particle accelerators, and the qubits of many quantum computers. Achieving room temperature superconductivity remains an elusive goal, but materials operating at ever higher temperatures continue to be discovered, holding promise for revolutionary applications in energy and electronics. Quantum networks could one day connect computers across the globe. Envisioned as the quantum analog of the Internet, quantum networks would link quantum computers, sensors, and secure communication nodes via entanglement and quantum channels. Photons carrying quantum information could travel through optical fibers or free space, establishing entanglement between distant nodes. Quantum repeaters, still under development, would extend range by correcting losses and errors without measuring the fragile quantum states directly. Such networks would enable distributed quantum computing, where multiple processors collaborate on a single task, and secure communication guaranteed by the laws of physics. Early prototypes connecting metropolitan areas have been demonstrated, and satellite links have extended entanglement across continents. Building a truly global quantum internet will require advances in hardware, protocols, and integration with classical infrastructure. The vision is ambitious, but progress accelerates each year. Atomic clocks keep time with extraordinary precision thanks to quantum effects. Modern atomic clocks measure time by counting oscillations of atoms transitioning between energy levels. These transitions occur at fixed frequencies determined by quantum mechanics, providing a natural standard unaffected by temperature, pressure, or other environmental factors. The best optical clocks today would neither gain nor lose a second over the age of the universe. Such precision enables technologies from GPS satellites to high-speed trading networks that depend on synchronized timekeeping across continents. Atomic clocks have tested Einstein's relativity by measuring time dilation at walking speed or across different gravitational potentials. They also set the standard for the second itself, defining the fundamental unit of time in terms of atomic transitions. Quantum mechanics does not merely influence timekeeping, it defines it. Quantum technology is already reshaping science and industry. Quantum mechanics is no longer confined to academic laboratories. Quantum sensors navigate submarines and map underground resources. Quantum cryptography protects government and financial communications. Quantum computers, still in their infancy, tackle optimization and simulation problems that hint at future capabilities. Techniques developed for quantum control improve medical imaging and materials science. Governments and corporations invest billions of dollars, recognizing that leadership in quantum technology may confer strategic advantages for decades to come. Startups and established companies alike race to commercialize quantum advantages. The transition from curiosity to application echoes earlier technological revolutions sparked by the transistor and the laser, both products of quantum understanding. The coming decades will likely see quantum technology integrated into everyday life, from secure communications to drug discovery to energy-efficient materials. The Copenhagen interpretation says reality is not real until measured. Developed primarily by Niels Bohr and Werner Heisenberg in the late 1920s, the Copenhagen interpretation remains the most widely taught framework for understanding quantum mechanics. It holds that the wave function does not describe an objective physical state, but encodes our knowledge of possible outcomes. Before measurement, a quantum system has no definite properties. Only when observed does a specific reality emerge. The act of measurement is fundamental, not reducible to any underlying mechanism. Critics argue that the interpretation is vague about what counts as a measurement, and where the boundary lies between quantum and classical worlds. Nonetheless, the Copenhagen view has guided generations of physicists, and continues to shape how quantum mechanics is presented in textbooks. Its emphasis on epistemology over ontology invites deep philosophical questions about the nature of reality. The many worlds view suggests every possible outcome actually happens. Hugh Everett proposed a radical alternative to the Copenhagen interpretation in 1957. In his many worlds interpretation, the wave function never collapses. Instead, every quantum event branches reality into multiple parallel histories, one for each possible outcome. When a particle's spin is measured, the universe splits. In one branch, the spin is up. In another, it is down. Both branches are real and continue evolving independently. Observers in each branch experience a single outcome because they themselves have branched. Many worlds avoids the mysterious collapse process, but at the cost of an ever-proliferating multiverse beyond observation. Some physicists embrace its elegance, others find the ontological extravagance unacceptable. Debates continue, but the interpretation has gained traction in quantum cosmology and discussions of quantum computing. It remains one of the most provocative ideas in modern physics. Pilot wave theory gives particles hidden paths to follow. Developed by Louis de Broglie and later refined by David Bohm, pilot wave theory offers a deterministic alternative to standard quantum mechanics. In this view, particles always have definite positions and follow precise trajectories guided by a pilot wave. The wave evolves according to Schrödinger's equation and determines where the particle can go, while the particle itself moves along a single path influenced by the wave. The approach reproduces all the statistical predictions of quantum mechanics without invoking collapse or multiple worlds. Critics note that the pilot wave must propagate instantaneously across space, raising questions about compatibility with relativity. Still, the theory demonstrates that quantum mechanics admits deterministic interpretations, challenging the assumption that nature is fundamentally random. Pilot wave theory remains a minority view but attracts interest for its conceptual clarity. Collapse theories propose that quantum states can end themselves. Objective collapse models attempt to explain wave function collapse as a real physical process, not merely an update of knowledge. These theories introduce modifications to the Schrödinger equation so that superpositions spontaneously and randomly reduce to definite outcomes, especially for large systems. The most famous example, proposed by Ghirardi, Rimini, and Weber, adds tiny random localization events that accumulate and cause macroscopic objects to behave classically. Such models make predictions that differ slightly from standard quantum mechanics, opening the door to experimental tests. So far, experiments have not detected deviations, placing ever tighter constraints on collapse parameters. If collapse theories prove correct, they would provide a unified explanation for why cats are never observed in superposition while electrons are. The search for collapse signatures continues at the frontier of precision measurement. Decoherence explains why quantum strangeness fades in large objects. Everyday objects do not appear to be in superpositions, yet the atoms composing them obey quantum rules. Decoherence provides a partial explanation. When a quantum system interacts with its environment, the delicate phase relationships that produce interference become entangled with countless external particles. Information about the superposition leaks out, spreading among environmental degrees of freedom too numerous to track. The system's quantum behavior effectively disappears from view, even though it is never truly destroyed. Decoherence is extremely rapid for macroscopic objects, surrounded by air, light, and thermal radiation. This explains why we observe chairs and tables as definite objects, rather than smeared probability clouds. Decoherence does not solve the measurement problem entirely. It shows why interference vanishes, but not why one outcome is selected. Still, it illuminates the transition from quantum to classical behavior. The measurement problem continues to puzzle physicists today. At the heart of quantum mechanics lies an unresolved puzzle. What exactly happens when a measurement occurs? The mathematical formalism describes smooth, deterministic evolution of wave functions, punctuated by sudden, probabilistic collapses. Yet the theory does not specify when collapse happens, or what distinguishes a measurement from any other interaction. Attempts to address this issue have generated the diverse interpretations of quantum mechanics, from Copenhagen to many worlds to pilot wave theory. Each approach sidesteps or redefines the problem rather than solving it to everyone's satisfaction. The measurement problem is not merely philosophical, it bears on practical questions about the limits of quantum computers and the nature of information. Despite a century of progress, no consensus has emerged. Some physicists believe the problem will eventually dissolve into a more fundamental theory, while others suspect it will remain a permanent feature of our description of nature. some wonder whether consciousness plays a role in collapsing reality. A few physicists and philosophers have proposed that conscious observation is required for wave function collapse. Eugene Wigner famously argued that only minds can cause quantum states to become definite. In this view, matter remains in superposition until perceived by a sentient being. The idea is highly controversial. Most physicists reject it because consciousness is poorly defined, and because unconscious detectors seem to produce the same results as human observers. Modern experiments show that recording devices and environmental interactions are sufficient to cause decoherence. Nevertheless, the consciousness hypothesis persists in popular culture and some fringe scientific circles. It raises deep questions about whether physics can ever fully explain subjective experience. While mainstream physics proceeds without invoking consciousness, the debate underscores the philosophical depths stirred by quantum mechanics. Quantum logic does not always follow the rules of common sense. In classical logic, propositions obey familiar rules. A statement is either true or false, and if A implies B and B implies C, then A implies C. Quantum mechanics challenges these intuitions. Birkhoff and von Neumann proposed a new logical framework in which the distributive law of classical logic fails. In quantum logic, the statement that a particle has a definite position and momentum simultaneously is not merely uncertain but undefined. The lattice of propositions about a quantum system has a different structure from the Boolean algebra of classical propositions. This has practical consequences. Reasoning about quantum experiments requires careful attention to which properties can coexist. Quantum logic remains a niche field, but it illuminates why quantum mechanics resists translation into everyday language. Words like "and" or "and not" behave differently when applied to superposition states. The universe may be fundamentally random at its deepest level. Most randomness we encounter in daily life is deterministic at a deeper level. A shuffled deck of cards seems random because we cannot track every shuffle, not because the laws of physics fail to determine the outcome. Quantum randomness is different. When a radioactive nucleus decays, no hidden variable determines precisely when the event will occur. Bell test experiments support the conclusion that quantum outcomes are fundamentally indeterministic. This genuine randomness underlies quantum cryptography. An eavesdropper cannot predict the key bits because nature itself does not know them in advance. Philosophers debate whether randomness is a feature of reality or a limitation of our knowledge, but the operational success of quantum random number generators speaks for itself. If our universe contains true randomness, its origin lies deep in the quantum fabric of nature. Quantum effects may bend the very fabric of space and time. General relativity describes gravity as the curvature of a smooth space-time fabric, but merging relativity with quantum mechanics suggests that space-time itself may be quantized. At the Planck scale, roughly 10 to the minus 35 meters, fluctuations in geometry could become significant. Space-time might be foamy, discrete, or subject to uncertainty relations, like those governing position and momentum. Some models propose that space is woven from entangled networks, while others invoke strings vibrating in extra dimensions. Observations of distant gamma-ray bursts constrain certain predictions about space-time granularity. So far, no direct evidence of quantum space-time structure has emerged, but the search continues. Understanding how space-time arises from quantum ingredients is one of the deepest challenges in theoretical physics. Resolving this puzzle could reveal the ultimate nature of reality at its smallest scales. superfluid helium can flow upward against gravity without friction. When liquid helium is cooled below about 2.2 Kelvin, it becomes a superfluid with bizarre properties. A macroscopic fraction of atoms condenses into a single quantum state, allowing the liquid to flow without friction and climb container walls. If you spin a bucket of superfluid helium, it forms quantized vortices rather than rotating uniformly. These vortices are thin tubes of circulating fluid, each carrying a precise quantum of angular momentum. Superfluidity was first observed in the late 1930s and explained using Bose-Einstein statistics. The phenomenon demonstrates that quantum coherence can extend over macroscopic distances. Superfluid helium has practical uses in cooling superconducting magnets and sensitive detectors. It also provides a laboratory for studying the quantum mechanics of many interacting particles. In superfluids, the strange rules of the quantum realm become directly visible to human observers. Bose-Einstein condensates behave like a single giant atom. At temperatures a fraction of a degree above absolute zero, certain atoms crowd into the lowest quantum state, forming a Bose-Einstein condensate. First achieved in 1995, this exotic state of matter demonstrates quantum behavior on a macroscopic scale. Millions of atoms act as a single entity, describable by one wave function stretching across the entire sample. Laser cooling and magnetic traps are used to reach the required ultra-cold conditions. Bose-Einstein condensates allow scientists to observe phenomena like matter wave interference and quantized vortices directly. They have become platforms for simulating complex quantum systems, from superfluidity to magnetism. The condensate's collective behavior provides insights that are difficult to obtain from individual atoms. The achievement earned Eric Cornell, Carl Wieman, and Wolfgang Ketterle the Nobel Prize in Physics in 2001. Researchers continue to explore these ghostly clouds for applications in precision measurement and quantum simulation. Studying Bose-Einstein condensates remains one of the most active frontiers in atomic physics today. The quantum Hall effect creates entirely new forms of matter. When electrons are confined to two dimensions and exposed to a strong magnetic field at low temperatures, they exhibit the quantum Hall effect. Discovered in 1980, this phenomenon reveals that electrical resistance takes on precisely quantized values independent of material details. The effect arises because electrons organize into collective states with topological properties, protected from disorder and impurities. Klaus von Klitzing received the Nobel Prize for the discovery, and the integer quantum Hall effect now defines the international standard of electrical resistance. Fractional versions of the effect, explained by Robert Laughlin, indicate that electrons can behave as if they carry fractions of their charge. These exotic quasi-particles have sparked interest in fault-tolerant quantum computing. The quantum Hall effect remains a fertile ground for discovering new states of matter, with no analog in ordinary materials. Topological materials host quantum states that resist destruction. Topological insulators and other topological materials possess surface or edge states protected by the mathematics of their band structure. In a topological insulator, the interior is insulating, but the surface conducts electricity without resistance under ideal conditions. These surface states are robust because destroying them would require a change in the topological order, which cannot occur through small perturbations. The discovery of topological phases has opened a new chapter in condensed matter physics. Materials like bismuth selenide host electrons that behave like massless relativistic particles. Research into topological superconductors aims to produce exotic quasi-particles called Majorana fermions, which are candidates for stable qubits. Topological ideas now influence fields from photonics to acoustics. Understanding and exploiting topological protection may lead to more robust electronic and quantum devices. The Nobel Prize in Physics was awarded in 2016 for theoretical discoveries related to topological phases of matter. This recognition underscored the profound importance of topology in understanding quantum materials. Quantum tunneling allows particles to pass through solid barriers. In classical physics, a ball lacking sufficient energy cannot roll over a hill. In quantum mechanics, particles can tunnel through energy barriers, even when their kinetic energy is too low to surmount them. The wave function extends into the classically forbidden region, giving a finite probability of appearing on the other side. Tunneling is responsible for phenomena ranging from alpha decay of atomic nuclei to the operation of scanning tunneling microscopes. It enables flash memory to store data and plays a role in chemistry, allowing reactions to occur at lower temperatures than classical theory would predict. The effect becomes significant when barriers are thin and particles are light, such as electrons or protons. Tunneling illustrates how quantum mechanics permits outcomes that classical intuition would rule out. It remains one of the most striking demonstrations of wave nature at work. Engineers exploit tunneling in devices ranging from tunnel diodes to superconducting circuits, making this strange phenomenon a cornerstone of modern technology. Stars burn because quantum tunneling makes fusion possible. The Sun's core reaches around 15 million degrees, hot by earthly standards yet far too cool for protons to overcome their mutual electric repulsion through classical collisions alone. Quantum tunneling allows protons to penetrate the Coulomb barrier and fuse into helium nuclei, releasing the energy that lights the Sun. Without tunneling, the Sun's fusion rate would be negligible. This quantum boost explains why stars can shine steadily for billions of years, despite modest core temperatures. The same mechanism powers hydrogen bombs and experimental fusion reactors. Calculations of stellar energy production rely critically on tunneling probabilities. Thus, the warmth sustaining life on Earth ultimately owes its origin to particles sneaking through barriers that classical physics declares impassable. Tunneling is not just a laboratory curiosity, but a cosmic necessity. Every sunrise is a reminder that quantum mechanics operates not only in laboratories, but also at the heart of every shining star in the universe. Josephson junctions turn quantum effects into practical circuits. A Josephson junction consists of two superconductors separated by a thin insulating barrier. Electrons paired into Cooper pairs can tunnel through the barrier, producing a supercurrent without any applied voltage. Brian Josephson predicted this effect in 1962, earning him a Nobel Prize. Josephson junctions form the heart of superconducting quantum interference devices, or SQUIDs, which detect magnetic fields billions of times weaker than Earth's. They also serve as the building blocks of superconducting qubits in quantum computers. The junctions generate voltage oscillations at precisely defined frequencies, enabling the most accurate voltage standards. Medical imaging instruments use skew-jolt sensors to map brain activity non-invasively. Josephson junctions exemplify how quantum phenomena originally studied for fundamental insight have found indispensable roles in precision measurement and emerging technology. Research continues to refine junction fabrication, pushing towards more coherent qubits and more sensitive detectors that will shape the next generation of quantum devices. Observing a system constantly can freeze its motion entirely. The quantum Zeno effect, named after the ancient Greek paradox, occurs when frequent measurements prevent a quantum system from evolving. Each observation projects the system back to its initial state, resetting its evolution clock. If measurements are repeated rapidly enough, the system appears frozen, unable to transition to a different state. Experiments have confirmed this counterintuitive prediction using atoms and photons. The effect arises naturally from the mathematical structure of quantum mechanics. Short time intervals yield tiny transition probabilities that are interrupted by each measurement. The quantum Zeno effect has potential applications in protecting fragile quantum states from decay. Conversely, an anti-Zeno effect can speed up transitions under certain conditions. These phenomena highlight how the act of observation fundamentally influences quantum dynamics. Watching too closely can, quite literally, stop time for a quantum system. Quantum levitation allows objects to hover above magnets. Superconductors expel magnetic fields from their interiors, a phenomenon called the Meissner effect. When a superconducting disk is placed above a magnet, it floats in stable equilibrium, supported by the repulsion between induced currents and the external field. If the superconductor contains defects, some magnetic flux can become trapped in the material, pinning it at a fixed position and enabling dramatic demonstrations of quantum levitation. Slight pushes cause the levitating object to glide frictionlessly. These demonstrations captivate audiences and showcase the practical reality of quantum phenomena. Maglev trains exploit similar principles to reduce friction and achieve high speeds. Research into high-temperature superconductors aims to make levitation practical at more accessible temperatures. Quantum levitation transforms abstract superconducting physics into a vivid illustration that quantum effects can reshape everyday technology. Some living organisms may use quantum tricks to survive. Recent research suggests that certain biological processes exploit quantum effects. The enzyme that speeds nitrogen fixation may involve quantum tunneling of protons. Birds navigate long distances using radical pair mechanisms in their eyes that are sensitive to Earth's magnetic field. The speed of certain enzyme reactions implies that protons and electrons tunnel rather than traverse classical pathways. While the warm, wet environment of a cell seems hostile to delicate quantum coherence, evolution may have found ways to harness it briefly. The emerging field of quantum biology investigates these claims, searching for signatures of quantum effects amid the noise of living systems. If confirmed, such findings would expand the relevance of quantum mechanics beyond physics and chemistry into the domain of life itself. Nature may be more quantum than we ever imagined. Understanding how biology exploits quantum phenomena could inspire new designs for sensors, catalysts, and medical treatments rooted in the principles of the microworld. Plants may harvest sunlight using quantum coherence. Photosynthesis begins when a photon excites an electron in a light-harvesting complex. That excitation must reach the reaction center efficiently, yet the path involves many possible routes through a network of pigment molecules. Experiments in the 2000s suggested that quantum coherence guides the energy along optimal pathways, explaining the process's near-perfect efficiency. The observation sparked surprise, because biological systems were thought too warm and noisy to support coherence. Subsequent research has debated the duration and significance of these quantum effects, but the initial findings catalyzed a new field. Whether lasting for femtoseconds or longer, even brief coherence could enhance energy transfer. Understanding photosynthetic quantum effects may inspire new designs for solar cells and light harvesting technologies. Plants, it seems, may have evolved to exploit quantum physics billions of years before humans discovered it. Scientists continue to probe these mechanisms, hoping to unlock secrets that could revolutionize renewable energy and sustainable chemistry. Some birds may navigate using quantum entanglement in their eyes. Migratory birds travel thousands of miles with remarkable accuracy, and one proposed explanation involves quantum mechanics. The radical pair mechanism suggests that light triggers the formation of entangled electron pairs in cryptochrome proteins in the bird's retina. The direction of Earth's magnetic field affects how these pairs evolve and recombine, translating magnetic orientation into visual information the bird can perceive. Experiments support the sensitivity of avian navigation to weak magnetic perturbations that classical chemistry cannot explain. While the extent and nature of entanglement in this process remain under investigation, the hypothesis has opened exciting new avenues in quantum biology. If birds do rely on quantum effects, evolution has produced a biological quantum sensor far more sophisticated than early physicists could have imagined. Such discoveries challenge the assumption that quantum phenomena are irrelevant to large, warm organisms. The study of avian magnetoreception continues to inspire researchers seeking to understand how nature exploits the quantum world in ways we are only beginning to appreciate. Tiny quantum fluctuations shaped the structure of the early universe. In the first fraction of a second after the Big Bang, the universe was unimaginably small and dominated by quantum effects. Fluctuations in quantum fields produced minute variations in energy density. As the universe expanded during cosmic inflation, these microscopic fluctuations were stretched to astronomical scales. They seeded the slight density contrasts visible in the cosmic microwave background radiation. Over billions of years, gravity amplified these seeds into clusters of galaxies separated by vast voids. The map of the cosmos we observe today is, in a sense, a magnified image of quantum randomness from the dawn of time. Precision measurements of the cosmic microwave background confirm predictions of inflationary models rooted in quantum physics. Thus, the grandest structures in the universe trace their origin to the tiniest quantum whispers. Those ancient fluctuations grew into all the galaxies we see today. After inflation ended, the density contrasts imprinted by quantum fluctuations continued to evolve. Regions slightly denser than average attracted more matter through gravity, growing over time. Gas collapsed into the earliest stars and galaxies, igniting nuclear fusion and filling the universe with light. The pattern of galaxy clustering observed by surveys matches predictions derived from quantum initial conditions. Computer simulations starting from these seeds reproduce the cosmic web of filaments and voids remarkably well. Observations of the cosmic microwave background and galaxy surveys together confirm that quantum fluctuations set the stage for cosmic structure. Every galaxy, including our Milky Way, owes its existence to a primordial quantum ripple. The universe's architecture is a monument to the power of the very small to shape the very large. Black holes must obey the rules of quantum mechanics. General relativity predicts that black holes trap everything, even light, within an event horizon. Yet applying quantum field theory near the horizon led Stephen Hawking to conclude that black holes emit thermal radiation and slowly evaporate. This Hawking radiation poses a puzzle. If information that falls in cannot be recovered, quantum mechanics' requirement of unitary evolution seems violated. Resolving this black hole information paradox has driven decades of theoretical research. Proposals range from information leaking out with the radiation to exotic structures at the horizon. String theory and holography offer frameworks claiming that information is preserved, encoded on the horizon like a hologram. Observational tests are challenging, as Hawking radiation from astrophysical black holes is far too weak to detect. Nevertheless, the paradox remains a crucible where our understanding of quantum mechanics and gravity must ultimately be reconciled. Cosmic inflation was driven by quantum principles. Inflation proposes that within a tiny fraction of a second after the Big Bang, the universe expanded exponentially, driven by a quantum field called the inflaton. This rapid expansion smoothed out irregularities and explains why the observable universe appears so uniform. The inflaton's potential energy behaved like a cosmological constant, propelling space apart faster than light could travel. Quantum fluctuations in the inflaton field became the seeds for cosmic structure. When inflation ended, the inflaton's energy converted into particles, reheating the universe and initiating the hot Big Bang. Observations of the cosmic microwave background support inflationary predictions, including the spectrum of density perturbations. The mechanism uniting quantum fields and exponential expansion remains a triumph of theoretical cosmology. Inflation offers a glimpse of how quantum phenomena shaped the universe at the earliest imaginable moments. Dark energy may be the energy of the quantum vacuum. The accelerating expansion of the universe is attributed to dark energy, a mysterious component making up roughly 70% of cosmic energy density. One candidate explanation is vacuum energy. The zero-point fluctuations of quantum fields should contribute a constant energy to empty space. However, naive quantum field theory estimates of vacuum energy exceed the observed dark energy by a staggering factor of 10 to the power 120. This mismatch, called the cosmological constant problem, is one of physics' greatest puzzles. Various mechanisms have been proposed to cancel or suppress the vacuum contribution, but none is fully satisfactory. Alternative models invoke dynamic fields like quintessence that evolve over time. Regardless of its origin, dark energy profoundly shapes the universe's fate. Resolving the vacuum energy puzzle may require new physics at the intersection of quantum mechanics and gravitation. Space itself might be made of tiny discrete units. In everyday experience, space appears smooth and continuous. Yet several approaches to quantum gravity suggest that at the Planck scale, about 10 to the minus 35 meters, space may be granular. Loop quantum gravity, for example, describes space as a network of quantist loops, whose areas and volumes can only take discrete values. If space is discrete, it could have profound consequences for how we understand motion, locality, and even the speed of light. Some proposals predict that photons of different energies might travel at slightly different speeds over cosmological distances. Observations of distant gamma-ray bursts have placed stringent limits on such effects without yet detecting them. The question of whether space is fundamentally discrete or continuous remains open. Investigating the texture of spacetime at the smallest scales stands at the frontier of theoretical physics. Future experiments and observations may finally reveal whether the smooth stage on which all events unfold is built from granular quantum threads woven at the most fundamental level of reality. The entire universe could be one vast quantum system. Quantum cosmology treats the universe as a whole, as a quantum object described by a wave function. This wave function encodes probabilities for different geometries and matter configurations. In this view, concepts like definite spacetime and observer-independent reality emerge only approximately. The boundary between classical and quantum becomes blurred at cosmological scales. Quantum cosmology grapples with deep puzzles. What determines the initial wave function of the universe, and who observes it? Proposals like the Hartle-Hawking no-boundary condition attempt to specify initial conditions without invoking external time. While experimental tests of quantum cosmology are currently out of reach, the framework provides a consistent language for discussing the quantum origins of the cosmos. It represents the ultimate extension of quantum mechanics from atoms to everything. Contemplating the universe as a single quantum system pushes the boundaries of both physics and philosophy, inviting us to reimagine our place in a cosmos that is far stranger and more unified than everyday experience suggests. Quantum gravity seeks to unite all of physics into one theory. General relativity describes gravity as the geometry of space-time, while quantum mechanics governs the microworld. Uniting these two pillars into a single theory of quantum gravity remains one of physics' greatest challenges. Near black hole singularities or at the Big Bang, both gravitational and quantum effects are strong, demanding a unified description. Candidate approaches include string theory, loop quantum gravity, and causal dynamical triangulations. Each offers insights, but none has yet been experimentally confirmed. The Planck scale, where quantum gravitational effects become important, is far beyond the reach of current accelerators. Indirect clues may come from cosmology, gravitational waves, or precision tests of gravity. Achieving a consistent quantum theory of gravity would reveal how space-time itself emerges from fundamental quantum ingredients. The quest continues to inspire theoretical physicists around the world. Success would represent one of the most profound intellectual achievements in human history, unifying all known forces under a single coherent framework. String theory proposes that particles are tiny vibrating strings. In string theory, the fundamental constituents of nature are not point particles but one-dimensional strings. Different vibrational modes of the string correspond to different particles, including the graviton that mediates gravity. The theory naturally incorporates quantum mechanics and general relativity, offering a candidate framework for quantum gravity. However, consistency requires extra spatial dimensions, typically 6 or 7 beyond the 3 we perceive. These dimensions are thought to be compactified at scales too small to observe directly. String theory has generated profound mathematical insights and connections between gauge and gravitational physics. Critics note that no unique prediction distinguishes string theory from alternatives, and experimental verification remains elusive. Despite the challenges, string theory continues to attract researchers as a rich structure, linking quantum fields, gravity, and geometry in unexpected ways. The framework has also spurred developments in pure mathematics, influencing fields from algebraic geometry to number theory. Whether string theory ultimately describes nature remains to be seen, but its impact on theoretical physics is undeniable. Loop quantum gravity suggests space-time is woven from tiny loops. Loop quantum gravity takes a different path to quantum gravity by applying quantum rules directly to Einstein's general relativity. The result is a description of space-time as a network of discrete loops whose intersections define quantized volumes. Space is not infinitely divisible. Instead, it has a minimum area and volume, roughly at the Planck scale. This granular picture avoids the singularities that plague classical black holes and the Big Bang. The approach respects background independence, treating space-time itself as a dynamic, quantum entity. Loop quantum cosmology, an application of these ideas, predicts a big bounce rather than a singular beginning. While observational tests are challenging, theorists are exploring possible signatures in the cosmic microwave background. Loop quantum gravity offers a compelling vision of a universe built from quantum geometry. Researchers continue to develop the theory, seeking ways to connect its predictions with observable phenomena that could confirm or refine this bold approach to the nature of space and time. Wormholes might be entanglement made physical. Juan Maldacena and Leonard Susskind proposed the ER equals EPR conjecture, linking Einstein-Rosen bridges, wormholes, to Einstein-Podolsky-Rosen correlations, entanglement. In this picture, two entangled particles are connected by a microscopic wormhole, too small to transmit classical information. The idea suggests that space-time connectivity and quantum entanglement are two faces of the same coin. If correct, it provides a deep insight into the nature of space. Geometry may emerge from quantum correlations. The conjecture sheds light on the black hole information paradox, suggesting that infalling and outgoing particles remain connected through the wormhole interior. While experimental tests are far off, the theoretical implications are profound. The ER equals EPR proposal unites two of Einstein's most famous contributions in a surprising quantum synthesis. It exemplifies how entanglement continues to reshape our understanding of physics. If future research confirms this connection, it would fundamentally change how we think about the relationship between gravity, space-time, and quantum information. Quantum physics may hold the key to understanding everything. Every fundamental force except gravity has been successfully described in quantum terms. The dream of a theory of everything would unite gravity with the other forces within a single quantum framework. Such a theory would explain black holes, the Big Bang, and the very fabric of space-time. Candidates like string theory and loop quantum gravity aim at this goal, but remain incomplete. The search for a final theory drives much of contemporary theoretical physics. Experiments at particle accelerators and observations of cosmological phenomena provide clues. Whether a complete quantum unification is possible, or whether nature resists such tidy descriptions, remains to be seen. The pursuit has already generated deep insights into mathematics and the structure of physical law. Quantum physics, born from puzzles about light and atoms, may ultimately reveal the universe's deepest architecture. The Standard Model describes nearly all known particles and forces. The Standard Model of particle physics catalogues 17 fundamental particles and explains 3 of the 4 known forces: electromagnetism, the weak nuclear force, and the strong nuclear force. It is a quantum field theory, treating particles as excitations of underlying fields. The model's predictions have been confirmed to extraordinary precision at particle accelerators around the world. The discovery of the Higgs boson in 2012 at CERN completed the picture. Quarks and leptons make up matter, while gauge bosons carry forces. Despite its success, the Standard Model does not include gravity or explain dark matter and dark energy. Neutrino masses, while now known to be non-zero, required extensions to the original framework. The Standard Model remains our most complete and accurate description of the fundamental constituents of nature and their interactions. Yet the Standard Model leaves many questions unanswered. Despite its predictive power, the Standard Model is incomplete. It does not explain why there are 3 generations of quarks and leptons, or why particles have the masses they do. The hierarchy problem asks why the Higgs boson mass is so much smaller than the Planck scale. Dark matter, which outweighs visible matter by a factor of 5, has no candidate within the Standard Model. The source of the matter-antimatter asymmetry in the universe remains unexplained. Strong CP problem and the origin of neutrino masses point to physics beyond current understanding. The model also tells us nothing about gravity or the nature of dark energy. These gaps motivate searches for new particles at colliders and through cosmic observations. The Standard Model is not the end of physics, but a platform from which deeper questions are asked. Every unsolved puzzle is an invitation for future generations of scientists to push beyond the boundaries of current knowledge. Dark matter interacts through gravity, but remains invisible. Observations of galaxy rotation curves, gravitational lensing, and the cosmic microwave background indicate that most of the universe's mass is invisible. This dark matter exerts gravity yet does not emit, absorb, or reflect light. Various candidates have been proposed: weakly interacting massive particles, axions, and primordial black holes, among others. Direct detection experiments deep underground search for rare collisions with ordinary matter. No signal has been conclusively identified, tightening constraints on particle properties. Collider searches seek dark matter produced in high-energy collisions. Meanwhile, alternative theories like modified gravity attempt to explain observations without invoking new particles. The identity of dark matter remains one of the biggest mysteries in physics. Discovering its nature would transform our understanding of the universe's composition and evolution. Every galaxy, including our own Milky Way, appears to be embedded in a vast halo of this invisible substance, shaping the cosmos in ways we are only beginning to comprehend. Supersymmetry proposes a hidden partner for every known particle. Supersymmetry is a theoretical extension of the Standard Model that pairs each fermion with a boson and vice versa. These superpartners, if they exist, could solve the hierarchy problem by cancelling problematic quantum corrections to the Higgs mass. Supersymmetry also provides natural dark matter candidates in the form of stable neutral particles called neutralinos. The theory predicts new particles that should appear at accessible energies, yet searches at the Large Hadron Collider have found no evidence so far. Increasingly stringent limits push superpartner masses beyond the reach of current experiments. Some physicists view this as a sign that nature may not be supersymmetric. Others suggest that superpartners may simply be heavier than hoped. The search continues, as confirming or ruling out supersymmetry would profoundly impact the future direction of particle physics. Whatever the outcome, the effort to test this beautiful theoretical idea demonstrates the power of experiment to adjudicate even the most elegant mathematical proposals. Extra dimensions may curl up too small for us to detect. String theory and other beyond Standard Model frameworks often require additional spatial dimensions beyond the three we perceive. These extra dimensions could be compactified, curled into tiny circles or more complex shapes at scales far smaller than any current experiment can probe. Some models propose larger extra dimensions that might affect gravity at short distances. Experiments searching for deviations from Newton's inverse square law have so far found none. Collider experiments have looked for signatures of extra dimensions, such as missing energy carried into the bulk of space, without success. If extra dimensions exist, they may reveal themselves through subtle effects on particle interactions or gravitational waves. The idea remains speculative, but offers a rich landscape for theoretical exploration. Their discovery would revolutionize our conception of what space truly is. The search for extra dimensions continues to motivate new experiments and theoretical studies, as physicists probe the limits of our understanding of the fabric of reality. The Planck scale marks the boundary where known physics breaks down. The Planck length, roughly 10 to the minus 35 meters, represents a fundamental limit in our current understanding. At this scale, both quantum effects and gravitational effects are equally strong, making predictions from either theory alone unreliable. The corresponding Planck time is about 10 to the minus 43 seconds, and the Planck energy is some 10 to the 19 giga-electron volts, far beyond any accelerator we can build. probing physics at the Planck scale directly is beyond foreseeable technology. Instead, physicists seek indirect signatures through cosmological observations and precision tests. Any complete theory of quantum gravity must make sense at this scale. The Planck scale thus serves as both a barrier and a guide, marking where our understanding ends and where new physics must begin. Reaching it conceptually is one of the grand goals of theoretical physics. The Planck scale reminds us that our current theories are approximations awaiting completion by future discoveries. Quantum effects may explain why time flows in one direction. In everyday life, time moves from past to future. Eggs break but do not unbreak, and we remember yesterday but not tomorrow. Yet the fundamental equations of physics, including quantum mechanics, are largely time-symmetric. The arrow of time appears to arise from the second law of thermodynamics: entropy tends to increase. At the quantum level, the irreversible growth of entanglement with the environment may underpin this asymmetry. Decoherence creates records and correlations that distinguish past from future. Some cosmologists argue that the initial low-entropy state of the universe is the ultimate source of time's arrow. Why the Big Bang began with such low entropy remains an open question. Understanding the quantum roots of time's direction could reshape our view of causality and memory. Time's arrow, familiar yet mysterious, connects thermodynamics, cosmology, and quantum physics. The arrow of time may emerge from quantum decoherence. Decoherence not only explains the classical appearance of macroscopic objects, but may also help account for why we perceive time as flowing forward. When a quantum system interacts with its environment, information about the system spreads irreversibly, creating a record of past events. This irreversible spreading of correlations mirrors the thermodynamic arrow of time. Attempts to reverse the process would require controlling an astronomical number of environmental degrees of freedom. In this sense, decoherence provides a mechanism for the effective irreversibility we experience. Critics argue that decoherence alone does not fully explain the arrow of time without invoking special initial conditions. Nevertheless, the deep connection between quantum entanglement and temporal asymmetry is an active area of research. Time's direction may be woven into the very fabric of quantum information. Retrocausality suggests the future might influence the past. Most physics assumes that causes precede effects. Yet some interpretations of quantum mechanics entertain the possibility that future events can influence the past, a concept called retrocausality. Time-symmetric formulations of quantum mechanics treat past and future on equal footing. The transactional interpretation, proposed by John Cramer, describes quantum interactions as exchanges of waves traveling both forward and backward in time. While retrocausality might help explain the correlations of entangled particles without faster-than-light signals, it challenges our intuitive notions of free will and causation. No experimental evidence currently favors retrocausality over standard interpretations. The idea remains controversial but continues to attract theoretical interest. If the future can touch the past, our understanding of time, causality, and reality would require profound revision. Some interpretations allow particles to travel backward through time. Richard Feynman proposed viewing a positron as an electron traveling backward in time. In Feynman diagrams, antiparticles are depicted as their corresponding particles moving in the reverse temporal direction. This is a mathematical convenience, but hints at deep symmetry between matter and antimatter. In the Wheeler-Feynman absorber theory, radiation arises from waves propagating both forward and backward in time. such ideas remain interpretive rather than predictive. Standard quantum field theory yields the same results without requiring literal backward time travel. Nevertheless, these frameworks illustrate that time's role in fundamental physics is subtler than everyday experience suggests. They challenge the assumption that particles must always move from past to future. Whether time travel remains forever fictional or holds physical meaning awaits deeper understanding. The quantum eraser experiment challenges our understanding of causality. In the quantum eraser experiment, entangled photons are sent along separate paths. One photon's path information can be recorded or erased, depending on the choice of measurement. Remarkably, erasing the information after the first photon has been detected can restore the interference pattern. The pattern appears or disappears depending on a measurement made later, seemingly reversing the order of cause and effect. This delayed choice quantum eraser does not allow sending signals backward in time. The interference only becomes visible when the two measurements are correlated after the fact. Nevertheless, the experiment highlights the non-classical nature of quantum correlations. It demonstrates that observed outcomes depend on measurement choices in subtle ways that defy simple causal narratives. The quantum eraser remains a favorite illustration of quantum weirdness. Information may be the most fundamental building block of reality. Some physicists propose that information, rather than matter or energy, lies at the heart of reality. John Wheeler famously summarized this with the phrase "it from bit," suggesting that every physical quantity derives its existence from information-theoretic yes or no questions. Quantum mechanics already treats measurements as information acquisition, and quantum computing exploits information as a computational resource. Black hole thermodynamics and the holographic principle hint that the universe's information content may be finite and holographically encoded. If reality is ultimately informational, then physics becomes a branch of information theory. This perspective has inspired new approaches to quantum gravity and sparked debates about the nature of existence. Whether information is truly fundamental or merely a useful description remains open. The idea invites us to view the universe not as a collection of objects, but as a vast network of interrelated data. Exploring the informational roots of reality promises to reshape our understanding of what it means for anything to exist. The holographic principle suggests reality is encoded on a distant surface. The holographic principle, inspired by black hole thermodynamics, proposes that all the information within a region of space can be encoded on its boundary. In this view, our three-dimensional experience emerges from a two-dimensional description, much like a hologram projects a three-dimensional image from a flat surface. The AD/CFT correspondence in string theory provides a concrete realization of this idea, relating gravitational physics in one space to a quantum field theory without gravity on its boundary. If the holographic principle applies to our universe, the true degrees of freedom may reside on a distant cosmic surface. This would revolutionize our understanding of space, gravity, and information. While experimental tests are challenging, the principle has become a cornerstone of theoretical physics. It hints that the familiar three-dimensional world is a projection of deeper, lower-dimensional physics. The holographic perspective continues to inspire research into the nature of spacetime and the resolution of long-standing puzzles in quantum gravity. Black hole information paradox remains one of physics' greatest puzzles. When matter falls into a black hole, what happens to the information it carries? Hawking's calculation suggests that black holes radiate thermally, eventually evaporating and leaving no trace of what fell in. If information is lost, quantum mechanics' requirement that evolution be unitary is violated. Various resolutions have been proposed, Perhaps information is encoded in subtle correlations in the Hawking radiation, or it is stored in a remnant, or the horizon has unexpected structure. String theory and the ADS-CFT correspondence suggest that information is preserved, but the detailed mechanism remains elusive. The paradox has driven advances in our understanding of black holes, entropy, and quantum gravity. It stands as a litmus test for any proposed theory of everything. Resolving the paradox would reveal deep truths about the marriage of quantum mechanics and general relativity. Physicists continue to debate and refine models, knowing that whoever solves this puzzle will unlock secrets about the very fabric of reality. Quantum mechanics has never failed an experimental test. Over nearly a century, quantum mechanics has passed every experimental challenge with flying colors. Predictions of atomic spectra, particle scattering, and magnetic moments match measurements to many decimal places. Bell tests have confirmed that local hidden variable theories cannot reproduce quantum correlations. Modern technology, from lasers to transistors to MRI machines, relies on quantum principles and functions exactly as theory predicts. No experiment has revealed a breakdown of quantum rules or a need for modifications at accessible scales. This extraordinary track record gives physicists confidence that quantum mechanics accurately describes nature. Yet the theory remains conceptually puzzling, and its interpretation is contested. The tension between empirical success and philosophical unease makes quantum mechanics one of the most successful yet enigmatic frameworks in the history of science. The equations of quantum physics predict outcomes with stunning precision. The anomalous magnetic moment of the electron, calculated using quantum electrodynamics, agrees with experiment to more than 10 significant figures. This is one of the most accurate predictions in all of science. Similar precision characterizes predictions for atomic energy levels, particle decay rates, and cross-sections of scattering experiments. The success of quantum field theory in matching nature down to the tiniest measurable details inspires confidence in its formalism. At the same time, such precision raises questions about why the mathematical structures of quantum mechanics fit nature so perfectly. Some see this agreement as evidence that we have uncovered deep truths. Others wonder whether an even more accurate theory awaits. Regardless, the predictive power of quantum physics sets a standard that any successor theory must meet or exceed. Yet no one truly understands what quantum mechanics means. Despite its empirical success, quantum mechanics remains philosophically mysterious. What does the wave function represent? Is collapse real? Are there multiple worlds? These questions have generated competing interpretations, none universally accepted. Physicists routinely calculate accurate predictions while disagreeing about what those calculations describe. Some take an instrumentalist view, treating quantum mechanics as a tool for prediction rather than a picture of reality. Others seek an ontologically clear formulation that explains what truly exists. The lack of consensus after a century of debate suggests either that we are missing a key insight or that nature resists easy interpretation. The interpretive puzzle motivates ongoing research in foundations of quantum mechanics. Understanding what quantum mechanics means, not just how to use it, remains one of the deepest challenges in physics. This enduring mystery ensures that quantum foundations will continue to attract brilliant minds, seeking answers to questions that touch the very heart of existence. Richard Feynman said, "Nobody understands quantum mechanics." Richard Feynman, one of the 20th century's greatest physicists, famously remarked that nobody understands quantum mechanics. He did not mean that physicists cannot use the theory. Rather, he acknowledged that its conceptual foundations remain perplexing even to experts. Feynman's statement captures a widespread feeling among those who work with quantum mechanics daily. The mathematics works, predictions match reality, but the intuitive picture of what is happening eludes us. This candid admission by a Nobel laureate reassures students and researchers that confusion is not a sign of failure, but a reflection of the subject's genuine difficulty. Feynman's contributions to quantum electrodynamics earned him the Nobel Prize, yet he continued to grapple with the theory's meaning. His humility underscores that scientific understanding is always incomplete. Quantum mechanics remains an open invitation to deeper insight. Feynman's remark has become an enduring motto for physicists, reminding them that curiosity and humility are essential companions on the path to knowledge. The quantum world defies our everyday intuitions about reality. Human intuition evolved to navigate a world of tables, trees, and tigers, not electrons and photons. Quantum mechanics describes a realm where particles can be in two places at once, where observation alters outcomes, and where distant objects can be instantaneously correlated. These features clash with our common-sense expectations built from daily experience. We expect objects to have definite positions whether we look or not. Quantum mechanics says otherwise. We expect causes to precede effects in an orderly manner. Quantum mechanics introduces strange loops and correlations. Learning quantum mechanics often requires unlearning previously reliable intuitions. The disconnect between quantum reality and everyday experience is not a flaw in the theory, but a feature of nature. The universe at its deepest level simply does not behave the way we expect. Embracing this strangeness opens the door to genuine understanding and reveals a cosmos far richer and more surprising than our limited senses could ever have suggested on their own. New discoveries continue to reveal deeper layers of quantum strangeness. The frontier of quantum research constantly expands. Recent experiments have demonstrated entanglement across hundreds of kilometers, pushed quantum computers to solve problems beyond classical reach, and explored matter in exotic topological phases. Theoretical work has revealed connections between quantum information, black holes, and space-time geometry that would have seemed fantastical a generation ago. The discovery of Majorana fermion candidates and the development of quantum networks point to revolutions in technology. Meanwhile, precision tests probe the limits of quantum mechanics, searching for deviations that might hint at deeper physics. Each year brings new surprises, confirming that the quantum realm still holds secrets. Scientists remain far from a complete understanding, and that incompleteness drives continued exploration. Quantum strangeness is not a closed chapter, but an ongoing story with many pages yet to be written. The next breakthrough could come from any direction, rewriting textbooks and opening vistas we cannot yet imagine. The quantum realm remains one of the greatest frontiers of human knowledge. Quantum mechanics has transformed our understanding of matter, light, and energy. It underpins the technology of the modern world and offers tantalizing hints about the ultimate nature of reality. Yet for all we have learned, profound mysteries persist. The foundations of quantum mechanics, its meaning and interpretation, remain contested. The search for quantum gravity continues. Dark matter and dark energy await explanation. New experiments and theoretical insights push the boundaries further. The quantum frontier is not a destination, but a horizon that recedes as we approach. Each discovery opens new questions, and each answer reveals deeper puzzles. The exploration of the quantum realm connects humanity to the smallest scales of existence and the largest questions about the universe. It is a journey that shows no sign of ending. Generations of scientists yet to come will continue unraveling the wonders hidden in the quantum fabric of reality, building upon the foundation that this century has laid. And now the quiet wonders of the quantum world, begin to gently fade into the stillness of sleep. You have wandered through over 100 peaceful truths about the strange realm that lies beneath all things. From particles that exist in many places at once, to entangled pairs that share their fate across the cosmos. From waves that become particles when observed to fields that bubble with invisible energy, even in the emptiest void. You have explored how the act of measurement shapes reality, how uncertainty is woven into the fabric of nature, and how the smallest scales of existence follow rules that seem to defy everything we know from daily life. You have learned that beneath the solid, predictable world we see, there lies a deeper layer of probability, connection, and mystery that scientists are only beginning to understand. You are connected to this story more deeply than you may realize. Right now, as you listen, quantum effects are holding your atoms together. Electrons are tunneling through barriers in your cells. Photons are carrying messages between neurons in patterns too subtle to notice. The very stability of your body depends on quantum rules that never sleep. If your eyes feel heavy now, let them close. Let the rhythm of your breath become steady, like the gentle oscillation of a wave function, like the quiet pulse of particles flickering in and out of existence in the vacuum of space. Tonight, as you rest, the quantum world continues its silent work. Particles will superpose. Entangled pairs will hold their bond. Virtual particles will shimmer briefly into being and vanish again. And somewhere in the depths of reality, the boundary between what is and what might be remains softly blurred. You are a small, warm presence within this vast quantum tapestry, peacefully resting among the wonders. Sleep well, sweet dreams. And may you carry with you the quiet knowledge that beneath every atom and within every moment, the universe holds mysteries deeper than we can imagine, waiting patiently to be understood. Thank you for joining me on this journey through the hidden world of quantum physics. If you enjoyed this video, please subscribe to Drowsy Discovery for more soothing explorations of the deepest mysteries of reality. There are more wonders waiting. More secrets hidden in the fabric of space and time. More gentle truths to drift through on quiet evenings. Rest well. And may the soft hum of the quantum realm keep you company through the night. This has been Drowsy Discovery. Good night.